Hey everyone, and welcome class to today's explainer. I am so excited you're here with us right now, because today we're going to absolutely demystify a foundational pillar of digital design. You know, if you've ever wondered how a tiny little logo on your phone screen can somehow be blown up to the size of a giant billboard without looking like a blurry, pixelated mess, well, you are exactly in the right place. So let's roll up our sleeves, step into the classroom, and figure out the mechanics behind this magic together, shall we? Okay, so here is our lesson plan for today. First up, what are vector graphics? Then, drawing with coordinates, followed by the power of scaling. After that, we'll look at vectors in the real world. And finally, we'll wrap up with a quick lesson review and a pop quiz. All right, let's dive right into this with section 1. What are vector graphics? So, what exactly is a vector? Well, simply put, a vector is a specific type of image that's created on a computer. But here's the kicker. Instead of being made up of a fixed grid of tiny little colored squares, which we call pixels, a vector is completely driven by mathematical instructions. Now hey, don't let the word math scare you off here. Honestly, just think of it as a set of extremely precise directions that tell the computer exactly how to draw a shape. It's not just some static picture, it's literally a live set of instructions. Actually, the absolutely easiest way to really understand this concept is to think back to a simple childhood dot-to-dot puzzle. You remember those, right? You have a blank page covered with numbered dots, and you basically just draw a line from dot 1 over to dot 2, down to dot 3, until suddenly a recognizable picture emerges. Well, a vector graphic follows this exact same principle. The computer is just acting as the pen, drawing lines between very specific points to build an image from start to finish. It's that simple. But that begs the question, how does the computer actually know where those dots belong in the first place? Well, that is where coordinates come in. Coordinates are the specific x and y positions on a grid, and they're always measured from a fixed starting point. So, the x-axis runs horizontally, side to side, and the y-axis runs vertically, up and down. These coordinates basically act as the actual map that tells the computer exactly where to place those dots for our digital dot-to-dot puzzle. Moving right along to section 2, drawing with coordinates. Let's look under the hood. Okay, so to turn those coordinates into an actual graphic, the computer relies on an algorithm. Now, an algorithm is really just a simple set of instructions required to generate that vector shape. It's basically the step-by-step recipe the computer follows. Think about it like baking a cake, right? You have to follow the steps in a very specific order. Drawing a vector requires the computer to follow a logical sequence in that exact same way. So what exactly goes into this recipe? Well, first, the computer needs a starting point, obviously, followed by an endpoint. Then it has to decide the type of line it's going to draw between them. After that, it calculates any necessary curves or angles. And finally, step 5, it fills in the line and the shape colors. And boom, just like that, a completely blank screen becomes a fully finished shape. Let's watch how this actually plays out in practice. Say we want to draw a blue line. The algorithm says, okay, start at x1, y1, and jump to an endpoint over at x2, y8. Make the line blue. Done. Now for something a bit more complex, like a yellow triangle. We start at x4, y3, plot a midpoint way up at x6, y9, bring it back down to x8, y3, and then fill the whole thing with yellow. See? By simply connecting those coordinate dots, a perfect, crisp geometric shape emerges. Let's do a quick little whiteboard summary here just to lock all this in. Remember, vector graphics are created using x and y coordinates. They follow a simple 5-step algorithmic recipe. And because of this incredibly precise math-based plotting, they are ideally suited for creating super crisp geometric shapes. Got it? Awesome. Let's keep going. All right, section 3, the power of scaling. Now this right here, this is the vector's absolute ultimate superpower. The absolutely crucial point to understand here is that a vector can be scaled infinitely. Let's say we start with a small yellow rectangle. If we want to double its size, the computer doesn't just stretch the image out. No, it just multiplies the math, expanding those coordinates perfectly. And the exact same thing happens if we quadruple it. The system literally recalculates the distance on the fly, which means the edges stay flawlessly crisp whether you print that rectangle on a tiny little postage stamp or project it onto the side of a massive skyscraper. So let's summarize the key benefits here for the class. First, as we literally just saw, vectors scale up or down without losing any image quality whatsoever. Second, because you're really just saving text-based instructions rather than millions of heavy pixels, the file sizes are remarkably small. Seriously, we're talking mere kilobytes for a really complex logo.
And third, because it's all just coordinates under the hood, they are incredibly easy to jump in and edit later on.
Moving on to section 4, vectors in the real world. So where do these graphics actually live in our daily lives? Well, vectors are actually a massive part of dozens of different industries. Take those classic retro Space Invaders, for example. Interestingly enough, a lot of early arcade games were purely vector-based, simply because the vintage hardware of the time just couldn't handle heavy pixel files. That brilliant foundational tech paved the way for the smooth, infinitely scalable graphics we take for granted today in modern console games. You're also going to see vectors absolutely everywhere in 2D and 3D television animation, feature films, and basically every single advertising logo or corporate cartoon character you've ever laid eyes on. To quickly summarize our industry usage, vectors really are the backbone of 2D and 3D television and movies. They're deeply, deeply rooted in the history of early video games, but they're still heavily used in modern consoles today. And for sure, they are the absolute gold standard for advertising logos and cartoon characters. Why? Because companies need their logos to look just as perfect on a tiny little business card as they do plastered on the side of a massive blimp. Which brings us to section 5, lesson review and pop quiz. All right, clear your desks. Let's see just how much of this lesson stuck. But hey, don't worry, you're going to do great. Okay, question number 1. How is a vector graphic algorithm like a childhood puzzle? I'll give you a second to think about it. Got it? Well, it relies on a simple start-to-finish dot-to-dot principle. Just like connecting the numbered dots on a page with a pen, the computer connects coordinate dots to build the final image. Moving on, question number 2. What happens to a vector's file size and image quality when it gets scaled up, say, 4 times its original size? Think back to our yellow rectangles for a second. The answer is the image quality never degrades, it stays perfectly crisp. And amazingly, the file size stays impressively small because the computer is just recalculating the math. And here's our final question, number 3. Name just 2 of the 5 specific algorithmic instructions needed for a computer to draw a vector. Take a moment. Okay, if you said starting point, end point, type of line, curves or angles, or line and fill colors, you are absolutely correct. Go ahead and give yourself an A+.
To wrap up today's explainer, I want to leave you with a little assignment for further investigation. I want you to look around you today and ask yourself, where else in industry could you see vector graphics being used tomorrow? You know, as technology evolves, so does the sheer power of scalable, math-based design. So keep your eyes open, keep learning, and I will see you in the next explainer.